subject research area, you can say. So this drive system actually it is completely depends on that embedded control system design, and hardware also it is included. So before starting, we just see that why do we need that controller and what are the important parameters to be controlled. So we have some machine or something, so any object. So we why do we need that control actually? So the control is mainly that it is depends to give some input and get some output from the system, and based on that output we have to give some corrective action to the system. And like suppose we run one vehicle. Okay, so we start running from one place, A point to B point. Okay, without visual we can't drive any bike or any car. Okay, so one point to another. So important sensor is like a parameter is one is that sight, visual. Without visual we can't move the vehicle one point to another point. And another one is sometimes we require some horn. Okay, some external signal input like uh, something burning. Okay, that smell is required. Okay, and sometimes like that signal I'm getting from the environment, like that hearing horn, somebody is hitting backside, or someone is I'm hitting. Okay, so or somebody is giving horn to me. Okay, so this kind of signals we required, this kind of parameters we need to measure, and based on that measurement we do that corrective action. What we need, driver do the driving. Okay, so this is one example. So any kind of system we require some input we can give the system. If I give some input, of course that system will give some response. Based on that response we have to give we have to reach our desired input level. Okay, so this is actually mainly we need the controller. Okay, so suppose that this is one vehicle or anything, it is a robot also. If you make this electrically or mechanical system, so one point, suppose this vehicle, if you want to move from one point to another point, so initially how much force is required? This is the net force we have to find. The point at the moment applied force will move the vehicle one point to another point. So this total, it is depends actually, we can calculate this force like one is the gradient. Okay, it is one angular inclination is there. So this gradient, one force will, reaction force will applied here, opposite force. Another is rolling, is the friction, the tire and that road, that frictional the force will applied here. So why I'm saying this one, because before applying any control system or any embedded system design, we need the full understanding of the system. So this is one system. That system, it is one total FTR is the total tractive force. That equivalent force I have to apply. So I need to know that which forces are applied here. Okay, so total force is one is the rolling frictional. Okay, from the road profile and the tire friction will come the rolling force. Another is the air drag and aerodynamic. Suppose it is a stormy season. Okay, so at the time I need to move the vehicle one point to another point. Okay, so little force is required more. Okay, so that opposite force is the aerodynamic force. Another one is like that air drag. Okay, and this is the great force. The total, this four type of main dominating force will apply here, which I have to overcome. So this total force, it is called the FTR, total tractive force. So this force can be divided like one is the theta. It's based on that cos theta. You will get this one ruling ruling force. Aerodynamic will get the that velocity of the wind and the coefficient, and you will get that total aerodynamic circulation depends on this circulation and aerodynamic profile of the body shape. You will feel some force, a negative force. And another force is the gradient force. It is a total weight and that sine theta. The acceleration, if you accelerate the system, so at the time you will get some drag force. Okay, acceleration, reverse acceleration force you will uh, experience. So that total force, you can say it is a measurable quantity. You can measure it or estimate it somehow, but sometimes we will get different kind of force also. Road profile, if it is a different uneven system, then also like rural and urban road, also road profile, you will get some different kind of forces. So this is the only thing, is that four types of measure forces you will get. You can calculate this total tractive force of the vehicle. It is not just only for the vehicle, it is for all kind of, even small system also, small system to big large system, heavy duty vehicle also, vehicle or any drive system. This vehicle is a good example of the electrical drive system actually. So because it is completely moving one body completely, one, yeah, like one cart pull system. So how much force is required? All this time, if we observe the one, just like Thela, no, that we just pull or push we the that cart, and we try to move one point to another point. So what it will do, that at the time we apply our own force. So we don't know what is that force, but we by based on the experience, we just give some force and it will move. But in case of vehicle design, so there is an engine is there, or maybe robot, some battery power source is required. So how much that force is required in the wheel, so that the full body can move one point to another point. This is the main tractive force. This is valid for any kind of movable system. Okay, if it is a flight, okay, so aeroplane, so at the time also, that ear drag, ear lift, how much lift is required, that time also we have to calculate all the forces. Maybe the component here in the means aeroplane case, it will increase some degree of freedom. That's why maybe it will increase the number of magnitude of the force, or vector dimension of the force. But conceptually, all the things are same. We have to calculate the net force to move one body one point to another point. So next, so these are the units. So next is a, okay, here I can calculate the force. This is a mechanical quantity. So this is the net force. But once I design the system, so I need that, based on that force, I have to calculate the total, how much power is required, how much energy is required, and what is the torque requirement. So that will, it will experience some load torque. Okay, finally this wheel will move one point to another point. So that rotational force, this force will convert to the rotational force, means the torque. So that torque again equivalent to the, it is coming from the shaft, engine shaft torque, and we have to apply proper amount of load torque to overcome the means we have to apply the motor torque or shaft torque, so that we can overcome the load torque. So that's why we have to calculate this total load torque we can get from this kind of relation. You will get some gear ratio if it is this transmission gear. So at the time you will get something, some constant value. But otherwise you will get gear ratio, means suppose first gear, second gear, third gear, how much it will come. Based on that, that gear ratio will come, and the net transmission, and this is the force and the radius of the wheel. You will get the load torque. This is the applied load torque. So I have to overcome, I have to apply greater than this load torque, then only the total body will move. So based on if once we know that load torque and the force, total attractive force, so we can instantaneously we can measure the power. So that force into velocity will get the power. So next, once we know the power, so that is the mechanical power it is required. So electrical power also will be the same. So same way that how much energy it is taking. So that this is the energy means that only that distance travel from one place to another point means at t1 second time and t2 second time, how much distance it's covered, and that the derivative of the total power means p into time. Actually power into time, you will get the energy consumption. So if once you get the energy, now for the robotic purpose or electrical purpose or this up to this much, it is the mechanical power. Okay, mechanical, that energy, how much energy consumption you are consuming that energy. But in case of robotics or any electrical vehicle, so you have to give the battery source. So that net amount of energy and the total transmission efficiency will get the net amount of battery. So practically you will get something like 1.11 times greater than the total consumed power. So means your battery, you have to select like that 1.11 times of that consumed energy. So then the system will be balanced. Okay, so because this quantity will become in zero point 0.9, suppose it is the highest uh, that efficiency is 0.9, 0.9, 0.9. So once I multiply all the zero point 0.9, so I will definitely get some smaller value. And so once the point less than less than 1 and is the divided quantity, so automatically it will increase. Means battery we have to select greater than the consumed energy. So this is the really fundamental relationship. So we need to understand to apply any kind of motor drives application. So next, if I observe, so suppose it's the electric, it is the IC engine based. Okay, so if we observe, this is the stroke, the four-stroke engine. But once we apply some uh, or we if we observe some pulse pulse rate, how much pulse rate it is coming. So we can see that at 3000 rpm we will get 25 pulses, okay, per second. Will receive this kind of pulses, one short pulse you will get. So continuously you will get one short spike, and because of that spike you will get the spark, and that spark will finally transmit to the rotational engine shaft rotation. Okay, so same thing if we observe, this is a mechanical system. Sometimes we are from the different background, like mechanical people can understand immediately, but sometimes the electrical people who are designing that hardware and the system level, and some software like IT or some electronics guys are looking for write the software, so how to apply that's replicate this system kind of thing. So at that time it's a very difficult to understand for them to total system and the actual implementation of the system. So here I can just give you the brief idea that this is the mechanical system, means that IC engine based system. Same thing if I convert in the electrical system, means that whatever the petrol I am giving or gasoline I am giving, so means they're replaced by battery. The source I replace the battery, and there is a some that duty here. It is spike kind of things. After a small duty, spike is observed here for the IC engine case. But here you can give some smooth. There is also spicer, voltage spicer. There means it is called the PWM switching frequency. What we know. Okay, so at the time we can see that continuously I can give lot of pulses here, and accordingly I can create some fundamental flux equation, just replicate the machine flux which will drive the motor rotation. So it is rotating. So one thing we can see that it is a fuel flow rate control. What I'm trying to explain here, like that one bike or one car, if I start accelerate the system, so what exactly we are doing? Accelerate the system means your rate of fuel you are controlling actually. So in the IC engine case, and if we observe for the electrical, so once we control the torque and the speed, we can see that we are actually controlling the current rate of change of the current. So if I change the current rate of change of value of the current magnitude or angle, phasor angle, if it is a DC motor, so just directly it is proportional to the current. So if we change the current, means my that torque also it will increase. Same way here, if I control the control the that fuel rate, so at the time I can control the vehicle speed or torque. Suppose it's the first gear, it is a reduce the speed and the torque I can achieve maximum. So like this here also we can emulate the system. So next I can see that this is the motor. Okay, it is a very abstract version of any mechanical system and the electrical system. So next I can see that this is also one dynamic understanding, that complete system. Previously we see that okay, this is the motor and this is the source. Now slowly I can go into the deep, like this is transmission box, means if it is CVT or any CVT gear system or any like a discrete gear system, like a one gear, two gear, three gear, four gear system. So there will be the transmission loss is almost, it is the 90 efficiency is 99 and 95%. So we can say that it is the lossless kind of things. We can neglect this loss. Okay, so it's a constant factor, and this is the wheel which is touching the ground. Okay, so I have to move this wheel to this direction. So now all the things I have given, like it is a robot system. Okay, I have selected one lead acid battery, I have given one controller. Okay, and this to drive this motor, so that the robot will move forward direction. Okay, so at the time, if it is a lightweight, it's fine. If it is a heavyweight like RoboWar, we use little heavyweight robot or robotic industrial robot, like robotic cart, like one point to another point you have to transport your all the materials from one point to another point, or one room to another room. So at the time we use this kind of heavyweight uh, robot. So this will give the idea that this is okay wheel direction, and this is exactly what I said the previously one equation, the total tractive force I'm overcoming. So it's a normal gear drag, grade resistance and rolling resistance, it will overcome, and there one load torque it will applied load torque. Now I have to control, I have to select the controller, or I have to give the instruction to the controller, the drive motor like that to overcome that load torque. So this is the fundamental system. So accordingly it will take the current from the battery pack, and it will try to move one point to another point through linear transmission, which will generated from rotational that body. So at the time I can immediately I can see that the control system I have to design for this kind of system. So what I will see, I'm an engineer, so first things we have to see that what is that total load here it is coming. So immediately I can summarize like this is a mechanical load. Okay, this mechanical load, I know the mechanical dynamics. Okay, rotational dynamics, I'll get some J d omega dt, that rate of change of mechanical speed in terms of total electrical torque minus this load torque and the frictional frictional some forces you will get that torque actually, that rotational and that frictional coefficient, so some shaft frictional and the total things, that b is the very low value, so we can neglect also, but for the time being this is the big system, we can assume that this is the big system, so some part it will be a perturbation will be there. Okay, so in that case, so equivalent inertia we know, if we know that the system I can immediately replicate. So this is the mechanical dynamics I'm getting from the mechanical side. Now from the electrical side also same way I will get some dynamics, like I know the torque equal to some cross product of the flux and the supply current. So this flux and the current is a vector, so definitely I'll get some dynamics of flux dynamics and the current dynamics. From that from this current dynamics and the flux dynamics I can evaluate the torque. So finally I can get some good mathematical relationships that electromechanical system and the energy supply. So finally I can, now the system is very easy for me. It is a motor, I know the motor dynamics. It is a mechanical load, I know the load dynamics. It is a controller, I know the hardware system inside sitting inside the controller, and what algorithm I have to write I know, and this is the battery pack, I know how much current and how much voltage I have to apply. So this is the main system. So now we can say it is a electric vehicle. Electric vehicle means just we are using terms electric vehicle, but actually it is if you observe in the mechanical means robotics, any robotics arm also, any industrial drives also, it is just like this one only. The battery pack means it is a standalone system. If I give some supply from the source, means electrical network source or system source, so this is just only the, instead of that battery pack I can give the source directly to the controller. And this motor is required to any motion control, we need one actuator, this is called the motor actuator, electrical actuator. So I have to control this actuator through mechanical through this controller, and to control the mechanical load. Now what is these things? The mechanical load means I know the system dynamics, so this one can give me one, if it is a known quantity, so I can predict the load and accordingly I can give the input. But if I don't predict this mechanical load, what will happen? Like for industrial you have one drilling machine. So what we know that if it is wall, we can immediately change the bit, the drill bit from for a wall we can use some different kind of bit, and for suppose it is the ms strongest material, so so we immediately change the bit for stainless steel. It is a different load. So we know that stainless steel is the material. Then we can use this kind of bit because we know the load pattern or load partial load form. We know the range of the load. We know it's a known load. So that is why it is called the industrial. Industrial means we know the load pattern. We have the idea. We have some observation of the load to drive this load to overcome or to get the sufficient amount of the force. We use directly motor load motor as a actuator for the particular mechanical load. So once load is known means it is an industrial drive system. Now, in case of it is the electric vehicle or aerospace modeling, okay, or aerodynamic modeling, you can say, or like spacecraft, okay, there you don't know the load. Only you know the prediction of load from zero, some bounded load, okay, some finite range of the load, but it is not exactly the same what you predicted. The prediction sometimes mismatch also. That is why our electric vehicle or any engine drive, okay, the car get accident, because we know the certain amount of load, known load, okay. So beyond that, definitely the system will collapse. So that's why accident happen. So the safety protection is much more required for this electric vehicle or like automobiles industry or spacecraft system. Because sometimes suppose the rocket I'm launching, and I know everything is fine, but it happens like one test, I was in NFTDC, so at the time I heard that one missile testing case. So some material inside the measurement was not proper. Very uh, few I think micron difference of the material inside the control system, it gets overloaded and the angle, it is just shifted. What is that? The trajectory angle, it is just shifted one by slightly the 0.001 degree resolution. It is changed and it is fall down. So that much risky the system. So these are not, is a small perturbation of load change, load disturbance means it's a huge change in the control system. So this kind of the heavy, highly high-end system, we need to design the controller like little advanced level control system we have to apply. So this is mainly the main system. Okay, so once you know the system, so your life is easy. You can immediately you can make your control system based on the understanding of the system. It is simple. It is, you can say, here I have written one equation, so maybe another two three equation or maximum fifth order model I can get from this system. Any robot system or any kinematic system I can get only fifth order model. But you imagine you are working with like twin rotor motor system. So twin rotor motor system, so what will happen? The twin rotor motor system means actually it is a helicopter. So helicopter means one rotor is the main rotor and another one is the tail rotor. So flight is, aeroplane is easier control system, but helicopter is the more tricky control system because it has, one is the uplift, downlift, and drag, forward drag, reverse drag. Okay, but tail rotor, another one is the creating the problem in the end, and based on the environment it is continuously non-linear kind of things. It's a one kind of memo system. You just imagine this kind of system like 15th order model or like 30 order model. So this is very tricky to design. Okay, robotics, small robotics arms we can design is very easily, but for this kind of system or like quadcopter, this quadcopter design also it is one kind of memo system. Okay, so it is a totally depends on the environment, and you don't know what is the environment situation is that right now and after 5 minutes what will happen in the environment system. Always you have to take the input from the environment, and accordingly your system has to be adaptive for this environment system. Like now you are using the GPS system to positioning your drone, but what will happen? Suddenly your GPS got banned. Means it is stopping signal receiving. So what will happen at that time? It will just do malfunction kind of things. It will lose the control. So at that time you have to design your control system like something intelligent system inside, so that it has to, even though GPS is for the, for sometimes it stopped receiving the signal, at the time also you have to design your algorithm such a way that it has to stable at the position. It should not violate, or it successfully it should land in your in the proper location. Okay, so this is the critical elements I'm telling. Okay, so next, this is the system. Once you understand, fully understand the system, you can implement your algorithm more elaborately. Okay, so next I can go more abstract version of this electrical drive system. Now see that this is the system. Battery is there, controller is there, motor is there, mechanical load is there. Okay, so I know the one system. But now here you see that one motor is there, like robotics arm. Okay, from 1 degree to 10 degree, one robotic arm always it has to move. Okay, like our knee joint. Okay, so you have to control this knee joint from one point to another point, the swing kind of thing. So at that time also, for to get this kind of swing, you need electrical motor. Okay, you have to control this motor, and definitely you are moving this motor means some load will be there, load dynamics. Okay, that mechanical load. Okay, so you will take the sensor input from the mechanical load, motor load. Okay, motor shaft, some speed or mechanical load. If you measure the directly torque, load cell torque, it is very good. You have the information, all the information. Power modular output from current voltage or something you were taking. Okay, this sensor input based on the sensor and the source also you were taking all the sensor information. Remember, once you know the all information about the system, means your control system will be more complex, but it will be robust and more dynamically response system. Okay, so control unit sensor input will take the data to the control unit, and control unit decide what kind of signal you have to, means control input you have to give to the power modular. Like if it is a suppose DC motor, so one DC-DC converter will be there. You have to control the DC-DC converter output. If it is a servo motor, you have to apply the servo driver. If it is a stepper motor, you have to apply the stepper, that asynchronous drive system. If it is the induction motor, three-phase motor, you have to give the three-phase inverter. If it is like something different BLDC motor, you have to apply the some three-phase inverter or a single-phase inverter. If it is single-phase BLDC, then single-phase inverter you have to give. Source, it is a battery or direct line drive source, or lithium-ion battery, lead acid battery, whatever you have given the source, it is a power supply. Okay, so if you observe this kind of system, directly we jump to this kind of abstract version. Okay, means uh, is the complete abstract of the skeleton of the system. Now why I am telling this one, this is the mechanical point of view or electrical point of view, but who those are writing the algorithm, they need to understand this way, that this is the power modulator, that inverter, you want to control this one, you need to understand the how to control this inverter. You need to understand the how to control, how to take the sensors from the motor, what type of motor it is connected, specification of the motor. If it is a your application is like for drilling machine application, industrial application, so you know the range of mechanical load. But if it is electric vehicle, you don't know the mechanical load, because it is completely depends on the road profile. Like you are driving in the Chandigarh road, so it is absolutely fine road. But if you're riding in our Tripura, some village area, so there may be not the proper road also. Okay, so it is a different, or maybe you are going to Sikkim, the road condition is very bad. Okay, so completely depends on road profile, the load, mechanical load demand also will be the different. Okay, so if it is the like a helicopter, okay, so a helicopter also same thing. You have to you apply some power modulator, and the motor is a electric helicopter or RC. Suppose you are RC, so now you are driving this helicopter in Arunachal Pradesh or Sikkim, and another one if you like I'm in Pune, Maharashtra, so if I drive this helicopter here, so in the same controller, so you will observe some differences there, because that Arunachal Pradesh or Sikkim or Himachal Pradesh, the environmental variation is too much. Means it is highly non-linear, unpredictable non-linear situation. But you can predict in Maharashtra or some Hyderabad or Bangalore, you can little predict the system. Okay, so based on that, this system you can say that is a more abstract version. Okay, so now those who are working in the sensor input, okay, so they can design their best sensor input. Those who are designing the control unit, they can write their best control algorithm. Okay, because they know the sensor input, what are the inputs. Once the motor is finally defined, so they immediately they can say that they can drive this mechanical load. Okay, so based on that input, they can design their power inverter converter. Okay, if it is a rectifier or DC-DC converter or AC to DC converter or DC to AC converter, or it is a frequency converter, anything they can design. Based on that, they can select their proper source. Okay, if it is a standalone system, so they can use the battery. If it is a line drive system like wind energy application, okay, so bidirectional system, like it is a solar application, they can use the solar source. Okay, so there may be another converter, but total thing is they're designing the source. Okay, this is the abstract version of electrical drive system. So next is now control of the power converter. It is very easy to understand that what we have to understand. Some reference we have given here, and suppose we want to control the flow of the water. Okay, so how, see that the example is, this is the one sensor. Okay, this sensor is a measuring sensor. It is taking the data. See that height is increasing. So this data I can observe, and this one is connected here, so that the water bulb, it is the outlet they can control. How? So once suppose is the B is the reference value. So this I gave the command to the system. Okay, that you stay at B point, not more than that, the water level. So it will no, then how we can understand? Okay, means this system, how can it will understand that I have to stay at B. So what you have to do, that this sensor value we are reading, and sensor actually you will get the information, and accordingly here one, that control bulb is there. So is a 50% open, means the 50% close the bulb. Okay, so is the control the output bulb. Now see that if control fails, what will happen? Of course, we have to see that we are designing the control. Okay, fine. Anytime we can design the control, but control fails, the safety protection. So how to do this one? Now I will put another offset limit A. Once it is cross the A or touch the A, immediately stop this bulb. So the way once it is stopped here, means here also that close, fully close that bulb. Okay, the signal you are giving means fully closed the bulb. See that it is stopped, the protection. Okay, so previously it was the B point, and secondly that is a fails the control, means it has to stop here, permanently stop. Okay, so this is the protection, means only thing is that you are not making the control system. Control system means it is you have to ask every time the question that what is the safety. Means there is two things are mandatory. One is that sufficient condition. Okay, the control is B, it will control the 50% opening. Okay, so it is a sufficient condition, but is it really it will sufficient? Means it is required the necessary. You have to prove your control system like 50% off means is a 50% off. If it is exceed, what will happen? Next question automatically it will come. So immediately the next question answer is that if it is touched, the B is a permanently off, shut down the system. Okay, this is called the emergency shutdown in the system. You will see in regularly you are using, suppose one instrument you are using, suddenly it is not doing the malfunction or it is uncontrollable. At the time, what you do? We do simply the switch off and switch on. Okay, computer also we do the switch on and switch off. So what is the meaning of that? The reboot the system or completely shut down the system. Okay, that our graphics table inside, it is if it is temperature dependent. If temperature is too much high and the cooling system is not working, so at the time of certain limit of temperature, it will just shut down the system. It will not allow to turn on the system. Okay, so I hope it is it is clear to everyone that what is actually the control system we are looking for. Okay, next, what to control? Okay, it's a planned input. See that the previous slide that I'm controlling this one. Now the question automatically what I'm controlling. Okay, is the flow rate of the water I'm controlling. This flow rate actually it is an input of the system. See that that's why the actually in the total control system, if we know complete the system dynamics, finally we have to reach what input we have to select to set the control system or regulate the system output. Okay, so this is the input of the plant. Whatever the plant you have designed, if it is a linear system or non-linear system or partial non-linear system. Okay, so only always you control the input parameter of the plant. Okay, next, the types of control. Now we know the control system we are applying. So two types of control generally we do. One is the regulatory control, another one is the tracking control. Regulatory control means speed control of the DC motor, because regulatory means I have given some desired value, desired reference, so that it will control the DC motor speed. So suppose it is the 300 RPM is the reference, so it will touch the 300 RPM. Okay, but tracking control like missile control. Okay, so missile control means target. I don't know what is the target, but I know the location mark. Okay, just I gave this a hit that flight. Okay, so I just launched the missile. What it will do automatically, it will track the trajectory. Okay, so automatically it will calculate the error from the target point. Error from the target point, always it will try to reduce the error. Okay, maintain the error. Okay, once is that zero and the nearby of the target point, it will just blast the whole aircraft or whatever the target point. Okay, so this is called the tracking control. Tracking control means you you just try to manipulate the error and the output based on error dynamics. Means error dynamics you were taking, rate of change of the error you were checking, and the error always you were trying to minimize. This is called the tracking control. Same way the regulatory control also, you were finding the error dynamics and reducing the error of the uh, desired value and the output measurement. Here is the only thing is that reference you have given, but in tracking control you can't give the reference because you don't know the reference. Okay, now it may be the some location, some xyz coordinate, Maybe next time some x plus delta x, y plus delta x, z plus delta x coordinate your system will be present. So what you will do, what reference you will give, you don't know anything. Okay, that's why just launch, and after that send the signal, real-time signal you send, just like a radar kind of thing. Means transmit the signal, reflect, receive, acknowledgement, and again transmit, receive, and acknowledgement. Based on that you are calculating. This is a communication problem, so you have to calculate the proper error dynamics model, and from this error dynamics you have to calculate the error minimization problem. Once the minimize the error means, and after some time it will hit the target. So this is like one example for regulatory. Like this is the plant. Okay, this is the control system, and this is the input reference, and this is the error. Okay, so now see that where is the disturbance. DS is the disturbance, means I say the speed control of the DC motor. Now this is the DC motor plant with mechanical also. You are taking output of the speed like speedometer you are using, or tachometer you are using to trace the output speed, and based on that you are taking some error, and you are designing one PI controller suppose. Based on that you are controlling, but what will happen at the time of disturbance. Okay, so disturbance means disturbance, some load torque you are applying. Okay, suddenly in the mechanical body some spring balance system suppose, or something you are drawing more current at that time. Okay, so mechanically you are giving some friction. Okay, so so that your system is disturbance, step disturbance you are giving. So a lot of types of disturbance you can give. So at the time your controller should stable. How you will find the stability? So means you have to design control system parameter such a way your closed loop control system must be stable. Okay, so this is called actually controller parameter design. So after that, once your control parameter, you will get some set of parameter. Now you have to tune the system. Okay, now physical system, it is a mathematical model. From the mathematical model you will get this kind of system, the very neat and clean signal. You know the disturbance pattern you are giving, accordingly you are giving the KPI, suppose PI controller, so KPKI value you are tuned. Okay, in the software, but in the real domain it will not like this exactly. At the time sometimes we say that whatever we have designed in the software, it may not work in the real hardware, definitely, because we did not calculate our noise in the system. Because one plant is the actual plant, we have modeled it as a linear system, but actually it is not linear. It is non-linearity is there, uncertainty is there, a lot of things are there. Okay, maybe 1 hour running, after 1 hour running this DC motor get later hot. So at the time what will happen, inside that winding parameter will change, so total model parameter will change. So what you will do? So means your system is changed. So previously in mathematically you have designed some control parameter based on P model, that PPS system plant model. But now it is a change in that after 1 hour the parameter is itself it get changed. So parametric uncertainty you will get here. So you have to overcome this one also. So now in the real time this condition also you have to satisfy. Sometimes it happens like morning I run the control system, it is working fine, but noon time I tried same control system for the same motor, it is not working properly. Why? It is because of the change of environment. Small motor, the small parameter you have given here, but in the noon time maybe it is a hot room temp, more than room temperature. You kept in outside in the uh, it's a sunlight. Okay, so you just change you what you will do, that at the time same controller if you apply, so it will not properly regulate the speed. You can see, you can do also that small example in any day. Okay, so to understand that non-linearity, uncertain parametric uncertainty in the system. Okay, this is one problem. Another one is the, you know, the disturbance you are giving, but you don't know that what kind of disturbance you are giving as a step, but step sideways there is some Gaussian noise, maybe it will come. Okay, so at the time also you did not take care about this this Gaussian noise also in the system. It is directly feeding to the system. Another one is the measurement. You are taking the measurement. Who knows that you are taking absolute parameter measuring output of the system? You don't know. Maybe some little offset. Suppose you are measuring 310 rpm, but you are giving the 300 rpm. So somehow it will lose the system. It will deviate from the system, and it will try to apply uh, some erroneous value to the control system. So mathematically, or mathematical model, if you have, implement in your, to understand the system configuration and the mathematical model, it is very good. If you apply more parametric uncertainty, if you include the nonlinearities, uncertainties, so you can see that your controller also it is changing the parameter, or maybe you require some adaptive type of controls, little robust type of control, not only PI controller sufficient for your system. Okay, so this is just one example. So like this is the schematic. You can see that functional diagram. Converter is there, DC motor is there, DC source is there, gate driver is there, electrical gate driver, and your microcontroller is there. So this microcontroller what will give that, you are writing one algorithm control system to speed reference and algorithm. Suppose PI controller you are applying. Okay, speed sensor is there. So you are controlling the current. So you are changing the load disturbance. See that suddenly you have given one load disturbance. So what will happen if you observe, like, see that kpk, if you change the gain of the system, if you observe that some different gains are there. So based on different types of load parameter, okay, this gain is continuously to required, it is adjust. So 190, 130, 160.2 is a three value I've taken. So one system I've simulated to understand that how it is changing. Okay, so it is not the 1k. Okay, but once in your real-time system, what will happen, you have to give, once you deploy your code, means your system is completely means implemented. You cannot change any gain value that time. So this is mathematically you are observing. So means your gain is not fixed. See 190, it is vary from 130 to 190, means something in between is, it is there. So you have to apply some robust kind of control so that it can adjust this disturbance range. Okay, this is small example. You can also do it. This is more required for your robotics purpose. Okay. So now the controller architecture. What is the fundamental hardware architecture? You see that hardware architecture. One motor is there, one inverter is there. It is the gate driver. This MOSFET or gate IGBT, if it is there, so it is like it is three-phase drive system. If it's a single phase, so H breeze is enough. DC motor, H breeze is enough. Okay, BLDC, if it is a three-phase inverter is required. If it is single phase, so single phase BLDC also it is there, like high speed BLDC, like drone motor. It is a single phase BLDC motor, high speed and high current also, high power, high torque actually. So so this is the protection system and the driver system to drive these MOSFETs. Okay, to drive this MOSFET, to give some pulses to the driver, is the just only that is some say low level signals. There is the high power application. Okay, it is a power main power board means inverter. This will drive the motor. To drive this MOSFETs or IGBTs, you require some driver. Driver means what it will do, like it is a low power system. See that it is flash, ADC, equip module, IO, RAM, CAN. So all the means total CPU is there. Okay, the sensor also you are taking, means that processor will take 3.3 voltage level or maximum 5 volt level. Okay, and the milliampere current rating. So total signals you are using the sensors, means you have to take the milliampere rating, maximum 500 milliampere suppose, and voltage is 3.3 to 5 5 volt system. Okay, so what will happen, that system, maybe it is a 20-volt system, 30 or 48-volt system, or 600-volt system. Okay, so like a high power grid kind of system. So it is a high power system. To drive this one, it is a this low power 5-volt system. To you are giving the proper gate signal. IGBT and MOSFET is required the gate input. Okay, that gate input is required. Suppose it's a 15 volt or 12 volt, okay, pulse, and some one, it is 100, so maximum 600 or 1 ampere maximum it is required. So this processor can't give. It is a low power device, completely low power device. If the frequency is high, the device power will be reduced. Okay, like it is a normal microcontroller like at mega or heavier, or like something uh, heavier, or some DSP or FPGA, anything you can use. Okay, but the power level, you see that if it is a 8-bit microprocessor, you will see that 5 volt. Okay, some current rating is high. Microprocessor, if you are using, means little higher current rating you will get. High sync, it is there, high sync current. Okay, but if you're using DSP, like floating point DSP, okay, so at that time what will happen, that it is a 3.3 volt or 1.6 volt maybe. So at the time the system what will respond, that system is reducing the power, because in your increasing DSP means you are increasing the clock frequency. Okay, 8-bit, any microcontroller, if you say 16 megahertz or maximum maybe 64 megahertz or 84 megahertz. But in DSP, more than it is the like 150 megahertz. Floating point DSP 150, 450 megahertz range it is there. FPGA is a more frequency is there. Okay, and you can, it is a complete digital design application. Okay, FPGA. So like this, depends on the system requirement, you have to apply your you have to use your microcontroller. So is a active, basically it is a low power. Okay, low power system. Now see that this low power system is required some gate driver which will drive the IGBTs or MOSFET to desired amount of like 15 volt or 12 volt or 1 ampere maximum. It will just convert this pulses, PWM pulses you are giving, that control pulses you have to convert in the desired value for the MOSFET and driver. Now this is the system. Okay, now this is the external parameter. What are those things? You are the input to the system, means throttle. You are, suppose your throttle or potentiometer, if you give the throttle or potentiometer, means it will change the duty ratio. Okay, it is a contactor drive, means it is a relay kind of things. If it is a relay, switch off the system, turn on the system, turn on or turn off the system. It is an external watchdog which will monitor all the times the inside the clocks and the execution. Okay, so this kind of system, it is a low power system. It is the current, voltage, temperature. It will measure speed, brake signal, speed detection. Okay, detection for acceleration, accelerate the system. Okay, and monitoring the speed. Okay, protection circuit like current protection, overcurrent, undercurrent, over voltage. Okay, under voltage, short circuit protection, this protection will come here. Okay, this is the hardware and software, hardware low power and medium power side. Okay, sensor and control unit. Now this CAN is connected to the, CAN means that communication area network, means it is a control area network, means it is that one CAN module can communicate with 32 another CAN devices. So like a vehicle system, it is a high-end system. Like you have the multi boards. Multi boards means the multi robots are there. So you have in a single place or single arena, and you have assigned like multi-agent system, like LIC agent. So you have lot of agents. Okay, 10, 20 agents you have, but you required autonomous communication system. You don't want to call them, you don't want to take the update from there directly. You will ask Satish, you give your update. Okay, you don't require. Okay, some XYZ, you don't require to ask any kind of information. What it will do, they will intercommunicate, and the master one communication will be there, that can protocol will applied for the all systems, so automatically they will update the system. Okay, if it is required to deploy the code, it will deploy the code. If it is required to access one agent system, so it will agent, and directly it will go to that module directly. Okay, so this is the flexibility of the CAN, and it is little faster than other communication protocol like SPI, SCI communication. The CAN is little faster communication and protective communication. Okay, so this is another auxiliary module. If it is required auxiliary module, so you can use the auxiliary module. So next is the auxiliary power supply. This auxiliary power supply means for driver circuit also required one power supply. For the sensor board and control unit is required also, microcontroller is required another auxiliary power supply. And another one is the battery source. It is also monitoring system is required. So like this, once you want to control all the parameters, means you have to design this kind of hardware architecture. This is a fundamental architecture. You cannot get other than that any hardware system. Here communication also there. If you want to build your communication system, you can use the IO is there. Okay, so any communication, Ethernet communication, converted the signal and use the IOs and GPIOs, or SCA communication, SPA communication. Okay, or any wireless communication. If you want to make, so you can make immediately. Okay, this is a you will choose the processor like this way. Okay, this is the hardware architecture of any drive system. Okay, next, that battery. Now what happened, you are using lead acid, so not required this kind of the control protection for the lead acid battery. We know everyone in Agartala city, I have seen that people are using like lead acid battery, and it is they're keeping their rickshaws in the outside in the rainy season, so no problem. But if it is a lithium ion, you need the battery management system. Means you have to you have to you have to sense the battery always, all the cell voltage you have to measure, and you have to check accordingly, because lithium ion battery is the one optimum point will give the proper output. If temperature is changed, increase the temperature or reduce the temperature, it will not give the optimized output. So this BMS is required, battery management system. What it will do, the management system, you can understand that it is the managing the output of the BMS. Okay, when it is required the charging, when it is required to calculate the SOC, all the things it will calculate. And this is also one active research area actually. So battery is sometimes short circuit. Let us say if you short circuit, so immediately short circuit, it will huge amount of current it will take. And if the voltage lower voltage means under voltage fault is there, so it will immediately, it will response time means it will control actually. Okay, disconnect the system. But lithium ion, it is not like this. If it is a short circuit, simply you will see that smoke is coming, and you cannot stop the fire for the lithium ion, like Tesla and uh, Tesla motors. One car just it gets burned in front of everyone. They can't stop the lithium ion battery current, means fire. Okay, so like another one is the Kona. So Hyundai Kona electric vehicle, it is also get blasted. So this only thing is the lithium ion they can't control. Once the temperature change or anything happened and hazard happened, so they can't manage the system. It will just simply blast. Okay, it is like bomb. Okay, so always you need to manage the battery. That is a for lithium ion battery. Okay. Next is embedded control system. So now up to this is the hardware architecture, everything we got. Next is the embedded control system. Embedded control system means like it is actually it is automobile industry, aircraft industry, and like civil structure. You are making like foundation, big foundation, big structures, architecture, manufacturing tools. Okay, household appliance. many other things you can use the embedded control system in everywhere. In everyday life we are using a lot of embedded system, embedded technique. Okay, so like automobiles, inside the automobiles one charger will be there, car one charger is there. This is also embedded control system because it is connected with the instrument cluster. Okay, that will give you the input, then only you can charge the your mobile or something. This is a protection level. Some cars are directly USB port is there, you can just plug and charge the your mobile. Okay, aircraft completely it is an embedded system. Okay, and civil structure, a lot of heavy industries are there, so some good PLC programming is required or advanced control system is required, so there is also embedded system, it is available. Okay, so next you can say characteristics of the embedded control system. We have studied in the theory that embedded control system is different, embedded system is different, embedded control system is different, but embedded control system and the total electrical drive system, without that embedded control electrical drive, okay, it is interdisciplinary things and it is required all sides knowledge. Okay, as a complete knowledge is required to develop one complete system. Okay, so that it is characterized, it is like interface with external environment. What I said, that it will take data, okay, from the external through sensors and actuator. Okay, distributed control network inside the processor, how it will distribute the control system inside embedded network or hardware system. Once suppose you were using the Ethernet protocol, so how that Ethernet protocol will work, or you were using some CAN communication, how that CAN will work. So that kind of distributor, what kind of signal, suppose you have suppose some 1000 or 1 lakh sensors inputters are there, so you have to distribute all the sensor input, and based on that you will design your distributed control system inside this pipeline. Okay, so next is the real-time critical system. Now the safety protection, that software must take care of this kind of system. Hardware protection, software protection must be required. Okay, without this critical analysis, critical that application, that you cannot design full your complete system. Okay, so you have to give the guarantee. Suppose we trust on Apple, my iPhone. Why? Because the hardware is too much optimized, but we don't want to use the China mobile. Okay, it's a today we are buying, and maybe after some days it will work or it may not work. Okay, that performance issue and the hardware engineering inside the software. So accordingly the price also you have to pay. Okay, you have to pay for iPhone something little higher price, and Android phone or some like China based mobile, Vivo, Oppo mobile, you have to give some it is not required much amount of the price. Okay, so this is the main three critical things for embedded control system. Okay, next is skills required. Okay, you are designing embedded control means one is algorithms, another one is the computer software, means apps. You have to develop your apps, real-time multitasking system. Okay, real-time operating system you have to design. Computer hardware, you have to understand which port, which interface, what kind of interface you are using, what kind of protocol you are using, memory. Okay, so ROM, RAM, you have to understand. Okay, next is, because computer hardware will decide you the host, because you have to write some code in the IDE or any Eclipse type of editor. You have to deploy your code, so it is required the hardware configuration. Okay, means computer hardware configuration, the protocol you have to properly understand. Digital electronics. Okay, digital electronics means you have to logical statement, you have to give, like fault. If 100 ampere current crosses, the system will shut down. Okay, so the comparator and a digital comparator will be there. Once pulse will be there, under voltage, over voltage protection, these are digital pulse only. It will give one, just one LED, it will glow, means it is digital status it is showing. Okay, now Another one is the sensors and actuators. Okay, so sensors is required, like in the vehicle, not only the motor controller, there is a lot of wiper is there. Okay, and horn is there. Okay, some intelligent system is there inside, like Toyota car, you will see there a lot of intelligent system inside there. Okay, like it's a cruise mode. Once it is the highway, so you just press the button, the cruise control, automatically it will set the one speed, and automatically it will go with a particular speed in the on the road. Okay, so next is mechanical design. So finally you have to come with a product design. Okay, so it should be not bulky, cost effective. Okay, so mechanical design, you have to understand, it should be robust. Okay, so mechanically stable system is required. Okay, like you are designing one DC-DC converter. Sometimes you will see that your electrical system is generating too much heat, so you have to design your heat sink. Mechanically you have to design, you have to give the cooling system properly. So mechanical design is required proper, otherwise that heat will block inside and it will get to, it will amplify that heat. Okay, multidisciplinary means actually is a multidisciplinary subject. Okay, so all the things, mechanical, electrical, computer, all the things you require to understand. Okay, the basic knowledge, fundamental knowledge is required to implement one complete embedded control system for electrical drive system. Okay, next is the industry trends is like, it is a industry day by day, it is completely, it is increasing the complexity. Okay, like previously we do the motor winding, like one man, okay, one or two man people are doing, person they are individually they are winding big motor or generator winding they do. But nowadays the autonomous system is there, Japan, German, what they are doing, they are using the robotics arm. Okay, faster system. Okay, faster way they can design their winding pattern. Okay, robotics manipulator they're using. Okay, so like this is a complexity is increased. So now see that once your uh, complex system if you are making, okay, so you, at the time you don't depend on the C code. You, if it is a 10,000 20,000 line C++ coding you are writing, so at the time what will happen, so once there is any mistake, 2,000 line 20,000 line, how can you check in the short time? Okay, so nowadays what happened, the model based embedded control software design also it is available, like MATLAB Simulink, state flow, auto code generation, rapid prototyping, hardware in load testing. So a lot of things are there. You need not worry about your library writing. Suppose you are writing a plus b whole square, okay, equal to y. Okay, so y is the function you are defining a plus b whole square. So it is not required to, it is a library you are generating, function library you are making. So it is not required to recreate. Okay, already a lot of people throughout the 20-30 years, people are doing research on that, and finally they are getting good libraries. Okay, so it is not much tough, and not means it's a preliminary things kind of thing. Okay, so you need not to implement again this code, and just use the code and higher level. MATLAB Simulink means it's the graphical user interface. Okay, you can drag drop the library and connection, you just concentrate on the modern control system. So once you're, if you see the industry, it is a complexity why they are increasing, because they can think much more what they want. Okay, so what you have to do, that MATLAB Simulink, autocode generation, these are highly high-end system, application specific design. Okay, uh, next is separation between control design and the controller. Okay, so one part is the control. We do sometimes like controller and control design, we, you know, both we are making in the same simultaneously. Okay, but industry they don't want to merge these things, because this both the things, controller is the complete things and the control design is the control algorithm design or some sub circuit of the system. Okay, so it should be sustainable in the embedded market. Okay, so because together if you make, so it may not be sustainable in the embedded market. Okay, so this is the industry trends. Okay, next is the embedded system design team. So once you are a manager, so you have to you need some skills to develop one team. Okay, how you will give the assign your work, okay, properly to develop to define one product, because one product design means it is not a single job for embedded system design engineer or drives engineer or maybe mechanical engineer. They can't individually, they can't do. Okay, means you need some application engineers, some hardware engineers, some software engineers, and they need to collaborate and they need to communicate each other, and they have to chase every times that what is going on. They need full understand of the system, how to make the system work in the product level. And of course, once the product is prototype is ready, means you have to concentrate in the price also, which component will select for to reduce the price of the system. Okay, so like this, which software algorithm you will use to get a good means uh, robust response from the hardware system. Application engineer, how to how best way you can communicate the system, you can marketize. Okay, so you can make the applications for different means you are designing one product and how it will uh, apply for different multiple purpose. Okay, if I design ones like servo motor drive, so I will design like servo motors and stepper motor also I can use. So like this means one drive system can handle servo drives and the stepper drives also. Okay, these are the main things to design one embedded team. Okay, finally, actually we have to start from this point. Team characterized embedded system, embedded drive system, complete system. It's the final things that team that will handle total product. Their responsibility is to make one total system. Even in the research also, you have to see that total one project you have to subdivide into small work and make the team like that, integrate all the work and get a good product. Okay, so now some applications like robot manipulator. See that how complex these things. Okay, if you see that one is a hinge is there, another one is there, another one is there, but if you see that structure, one, it is a non-linear things. It is depends on this one, this one is depends on this one. So every time theta 1, theta 2, theta 3 is a three angle, and the it can move in the xyz coordinate. Okay, so again there is another motor is a xy base is there. Okay, so this is robot manipulator. So you have to calculate, find the dynamics of the system accordingly. Complex algorithm you can, adaptive algorithm you can design, so that it can use for uh, taking like suppose it can serve your tea. Okay, design one program, write the what kind of motor you will use, you have to select. Okay, so it is just simply see that is a hinge joint and angle it is angular movement is theta 1 theta 2. Okay, bidirectional theta. So definitely we have to use stepper motor or servo is cheaper than stepper motor, so we can go with the servo motor, and the smooth control system you can design. Okay, next is one application is the robot. Okay, is a autonomous obstacle detection robot. Okay, these are the all our products actually. So this is my own build robot. So this one is obstacle detection algorithm, it is implemented here. So this is one servo motor is there, so it will see, and if any obstacles is there, this head will move just like human head, it will move, and accordingly that signal will pass through the wheel, and it will just move one point to another one direction, so it will never hit. Okay, this one another is the DC motor speed controller. Okay, DC motor speed controller, it is inside that motor is DC motor. So how it is connected? The hardware system is the measurement is the voltmeter, it is there, or multimeter. Okay, in terms of voltage, actually you are measuring the speed. Okay, so 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 it is like system. So amplifier, it is there, low pass filter, PWM is there. Okay, so you can control this one. Stroboscope means you have to see the RPM in the real time. Okay, this is the vehicle dynamics, the software, whatever I told you, that total system you can implement in the MATLAB, and finally you can deploy in the hardware system. Okay, this is another one is the that audio amplifier means why it is required, because you have to understand about the analog and the PCM and the PWM output. Okay, so PCM and PWM means the conversion of analog, and again you can reconstruct the signal through that your amplifier. Okay, so this is another product. Okay, it is a audio amplifier. So this is the same things, is the hardware prototype design. Okay, so this is 4-axis servo and stepper motor control drive system. This is industrial product. Okay, so in the 4-axis way you can control this one. 4-axis machine, 3-axis machine you can control. Okay, this is one another induction motor controller, 6-layer PCB design. It is in-house, it is designed. Okay, our design. Okay, next is the PMSM controller. It is a high a IGBT based. It is a 600 volt system. Okay, so these are the applications. Okay, so I hope I took some little time. Okay, so anything?
Thank you, Dr. Malakar.
Yes.
Thank you for a valuable presentation, and also you shown us the basic overview in which sense the industry is working now. Now
Yes.
the session is open for questions. If anyone has any question, you can
Yes.
ask. Okay, I guess
Okay.
currently they have no any questions. But
Okay.
if anyone have any questions, Dr. Malakar's email ID is with me. You can just contact us and we can share the email ID also.
Okay, anytime, Dr. Bishanko, anytime they can contact with me, or you just forward uh, whatever they want. Okay, thank
Okay,
you.
okay, okay. Thank you for their valuable presentation. Thank you, Dr. Malakar. And one information is also for the participants. The feedback form has been shared in the chat box. Kindly fill this as soon as possible. And after submitting this, your e-certificate will be dispatched in your email.
Thank you, Dr. Malakar.
Okay, thank you, sir.
Thank you.